Langenheim and colleagues at the USGS who modeled these data basically came up with a similar interpretation in their modeling of the gravity data. So I'm going to show you a gravity model cross-section that extends from the Hosby Fault out here across the Irish Hills, and it ends, I believe, at the Los Osos Fault here to the north. Okay, so this is the gravity anomaly. Again, starting out here in the offshore area from the Hosby Fault. This is the Shoreline Fault, San Miguelito Fault. This is the Edna A Fault, and this is the Los Osos Fault. You see this nice 25 milligal or so gravity low associated with the Pismo Basin. But in order to model this low, the modelers, Langenheim et al., put another fault that across which, or that juxtaposes higher density Franciscan rocks against a thick section of the lower part of the tertiary units of the Pismo Basin. And this is equivalent to the Edna C fault that we have interpreted. Now they have interpreted as a steeply north-dipping fault, but I would hazard that the gravity data could be equally modeled by the very steeply dipping south-dipping fault, similar to the Edna C that we've identified or interpreted in the reflection data. And then I just also wanted to briefly show you one of the images that Dan showed of the relief on the isovelocity surfaces. So the next slide I'm going to show you, we're going to be hovering above the Pacific Ocean, looking to the southeast across the Irish Hills and across the Montagna de Oro. Okay, so this would be Montagna de Oro right through here, and we're looking across the Irish Hills. And I think Dan made this point very well. I'm not going to go into it in detail, but that the first order geometry of the basin that we've interpreted from the reflection data, specifically the locations of the Edna B and Edna C faults that drop the basement down, and then the antithetic north-dipping faults where the basement steps up to the north, are captured in or reflected in the velocity and density structure as it's been modeled. Okay, finally, I'll just show you one more cross-section. This cross-section here that goes through a little closer to the plant, and I'll show it. It goes from just south of the Shoreline Fault and across the Los Osos Fault. This cross-section is drawn to a greater depth. It's drawn to the interpreted base of the brittle elastic crust, just to show how the down-dip geometry of these faults may continue to depth. And I should mention, I want to point out that we have interpreted a possible south-dipping fault up here beneath the southern part of the Irish Hills. This interpretation is driven primarily by the observed thickness of the lower part of the Obispo Formation, the map view, and then our interpretation of where the top of the basement is in line 141 and 142. And so if we've made a mistake in how we've projected this geology to depth, or if we haven't properly interpreted the top of the basement, then this fault would go away. But we haven't actually observed this fault in any of the reflection data or interpreted. Okay, this is, let me just back up and say the next slide is going to be a version of this cross-section, except what we've done is we've flattened it out. We've removed the tilting and folding in the shallow part of the stratigraphic section, just to show that after you remove the broad synformal folding of the Pismo Basin, undo the Pismo syncline, this is the restored geometry in our interpretation of the ancestral Pismo Basin. And this I think is a very plausible predeformed geometry, and it bears some similarities to examples from the onshore Santa Maria Basin to the south, which developed at about the same time in the same tectonic setting as the Pismo Basin. So we think that the structure that we've interpreted here is very similar and can be compared to an analog in the onshore Santa Maria Basin to the south. So to summarize the structure of the Irish Hills, the axis of the Pismo syncline we have interpreted from the reflection data to be underlain by north and south dipping normal faults. These structures form an intergraben that accommodated subsidence in Miocene time. The Edna Fault Zone is a series of right-stepping, steeply south-dipping normal faults that comprise the northern structural margin of this ancestral basin. The San Miguelito Fault Zone is a series of subvertical to steeply south-dipping faults with north-down stratigraphic separation. Our preferred interpretation of these structures were probably part of the ancestral southern basin margin, and they've been rotated to steeper dips as part of the uplift and tilting of the southern limb of the Pismo syncline. And the San Luis Bay Fault Zone is a north-dipping thrust or reverse fault. And then just to return to the slide that we saw earlier, this is the fault geometry that we've interpreted from the reflection data and reported out in our report. That's it. Thank you.
Don't know if I have a question for you. I think I started off with one of my questions I had in response to Stu's introduction or Steve's talk. This seems to me to be a complete and consistent and plausible story. Of course, it's required.
Yes. Thanks.
The question is it unique, and how many other complete, consistent, and plausible stories can be made? And I think we heard at the beginning that the TI team for the shack has a couple of other models that they're including and going forward with. Is there anything in these interpretations that you've showed us? Now, this is all leading up to an interpretation of a development of the tensional basin that's exposed transpressionally, which is consistent with their outward vergent model. Your interpretation doesn't go into the plausibility of the southward vergent model or the northward vergent model. And did you rule those out completely early on, or how did you go through that?
Well, we didn't explicitly address the shack models. Our charge was to interpret the data under AB 1632. The shack effort is completely separate.
Okay.
What we did as part of the evaluation of data, we did look at alternative ways of large-scale structure that we might come up with to explain this.
And there have been models presented in which most of that is explained through thrusting rather than by development of a basin.
We considered the thrust model, indeed.
And went through those. And what do you think is the best data you have to say that that's not favored interpretation over what you just presented? What's the main reason you favor this one over that?
The first order basin geometry, the fact that the gravity, velocity information indicate that it's primarily narrowing downward underneath the axis of the Pismo syncline. I think that we didn't explicitly and in detail try to do this, but if you were to try to come up with a thrust model for this, you would want to explain a couple different things. Why the thickness of the Obispo formation is so much greater in the core of the Pismo, in the tidewater well, but then how you can get 8,000 feet or more of structural relief on the basement. And geometrically, I don't think I don't think geometrically you could come up with a very plausible model to do that by thrusting. At least I would be interested in seeing somebody develop a model like that and then develop a restored model that undoes all that displacement, restores the top of the basement and to some sort of plausible predeformed geometry, and also accounts for the fact that the Pismo formation is kind of like a datum or a marker. You know, it sits on top of the Monterey on the south side of the Pismo syncline. It's on top of the Monterey on the north side. And so if you're undoing a bunch of thrust displacement, then you're going to have to pull that way down and distort the predeformed geometry. So we did think along these lines, and I think that this is the simplest and most straightforward explanation to pull together all of the data that we looked at.
I'll make an observation, editorial comment. All the lines of argument you just laid out, the digital field data, the electrical cross sections, the stratigraphic thicknesses, in addition to the geophysical data. The geophysical reflection data is not one of your strong arguments for or against any of these models.
It's important to developing a model.
And one of the discontinuities I have in reading these chapters is it says, here's all of the geophysical data with all of its uncertainties, and all nicely laid out, and fully acknowledge all the uncertainties and alternate interpretations. And then it says, and here is the interpretation from this geophysical data, which does not really do justice to what you guys have done, which is not primarily based on the geophysical reflection topography data. It's a structural, stratigraphic interpretation of what you've got. I mean, it's a plausible story based on all of your data, in which the geophysical reflection data is a component. And I think that is not well reflected in the writing. And so it's, this is,
Okay.
I'm getting nods and shakings of that. But this is something that, to me, reading this report, you get all the way through the expression of the reflection seismic data, and then there's a discontinuity with a very positive conclusion. And that positive conclusion, I think, is as positive as it is because of all this other data, which is not fully explained in this report. And so it's tough to follow. You get to the same conclusions from that report that you present in the text. And just want to make, as you explain it there, and I know you've gone through all these other analyses too. So it's the conclusions are more positive than the geophysical data allow, and I think it's partly because you're bringing in these other things, and I think it's partly because you're interpreting things I keep looking at, and I haven't had near as much time to listen to that as you guys. And I'm saying, I don't see that, and I don't see that either. And that's, what else can you do there? And so there's alternate interpretations that are allowable within the data. There's numerous other ones allowable within the geophysical data, and I'm not convinced there are also other ones allowable within all of the data considered. So that's kind of where I'm sitting right now.
And I would submit Chris is being charitable as regards to seismic reflection data. I don't think it constrains much of anything, frankly, in that interpretation. So let's separate the seismic reflection data from other geophysical data like the gravity data, which is a perfectly legitimate means of examining the structure of the Earth. It has its own set of limitations, and certainly nothing like the resolution nor the ability to constrain uniqueness that a properly imaged seismic reflections section, if you have appropriate controls. And we spoke to a relative, almost complete lack of well control, aside from a couple of points, and difficulty in tracing to the surface. And in fact, the report is explicit that these reflection seismic data don't rule out repetitive thrusting as a model for as a model for the structure of the basic physical parameters, let's say, of the pismal syncline. I think it would be incumbent on PG&E to demonstrate in some other fashion that the interpretation that you put forward, which are these normal faults, is is somehow to be preferred from this alternative that's explicitly acknowledged as possible there. And again, we've discussed here and elsewhere, again, if the reflection seismic data are to be used in any significant means of supporting this interpretation, I think there needs to be a very serious re-looking at the processing, the acquisition parameters, and how those acquisition parameters, which are acknowledged to be problematic, fit into the ability to interpret that image. Because quite frankly, I think you have great possibility of seeing lots of energy that shows up on those sections coming from far outside of where those 2D cross sections are put. I do not see the correlations. We talked about where you can draw faults, but aside from that, am not convinced of the correlations as you show basement stepping down, and there's no control. There's nothing. In a typical industry standard interpretation of a well field or a potential oil field, you would have a lot of other controls that you could apply to this, and this just isn't there. So I find it hard to buy from what I know of the geology of the Franciscan Formation to see the kind of lateral continuity that is interpreted out of the seismic reflection data. That's, to me, at least as probably an artifact or a particular bias in the reflection technique. And we've talked about what kinds of biases the actual experiment can put on seeing continuity, but that kind of continuity in the Franciscan doesn't make sense with what I know about its geology. So, I think it's fine to construct models, work at reconciling them with the Shack models and all those things on other bases, but I just do not see the support in the seismic reflection data for any preferred alternative.
So Bruce, if you saw those reflections in the shot gathers, direct, just applying the statics, no other doing maybe a time correction, and you saw them in the shot gathers, no other process. Would that convince you there's actually reflectivity there?
Well, there's obviously reflectivity, but that reflectivity doesn't necessarily come from the plane of the source receiver.
No, where we have 3D coverage, because I showed you that is where I have 3D coverage. We migrated, we have coverage 360 degrees there.
Well, and
we got the nodes out, we got the receivers out.
So, well, I would like to see the common midpoint fold. I'd like to see the variation in fold from one place to another.
So the fold is 100 to 300.
Well, again, that's a single statistic over a very complicated wave field. The application of statics to dive way down into the weeds is a simplification of how you correct for the near surface. Basically in this near surface, you're looking through a piece of shower glass, right? And we've talked about that. You're looking through the ripples of the shower glass. And the statics correction assume that you can simply move the recording by a particular amount, when in fact there's a very complicated transformation of the wave field as it comes through that very difficult near surface. So in order to validate the use of the reflection seismic data, there's a whole lot of independent review of it that I'd like to see.
Yeah, and that's all tractable. That's what I'm saying. We couldn't go into all the geeky weeds about how we did this, but we didn't have to do. We do a lot smaller scale residual statics than most people because we did so much shallow velocity, so that we didn't put it in the static. We physically put it in the model on topography. Right. So it's possible. I mean, seriously, we didn't do any residual statics on reflectors. Okay, none, zero.
Well,
we calculate the statics on the first breaks only.
Well, and that affects the reflectors. But for instance, you talk about.
As I said, since we did a lot more shallow modeling than you do in industry, right, the scale of the residual static just on the first breaks, and they're surface consistent, and you can look at are they biased? What is the scale of them?
Well.
So,
and again, we do a full review of that. You have to have a very detailed velocity model of the near surface in order to back out the wave field effects as that wave comes through. and you look at those two, there were two lines that you showed that were sort of, I guess, going over the Pismo syncline. They were offset by a little bit. So if you had really good 3D data, why didn't we have one long continuous line there?
No,
And
that's what I said. I broke them because I had 3D,
Right.
over a wider swaths to the north.
Right.
And then, because, you'd have to look at the map. You look at the roads that,
Right.
we were confined to for the sources, and then you sit there and you look at.
All understood, but
Yeah.
again, with that swath, and we talked about that before, did you have a sufficient cross-line aperture to
Yeah.
actually image out those things? And if so, we gotta analyze that was the case, because the resulting section looked very heavily filtered to my eye.
Yeah.
Adjusted for lots
I
of
can see how
things.
you can see that, but I can break it down into component pieces, and, a lot of effort went into getting the cross-line aperture through that area. So, I calculated, rigorously, the azimuthal and offset bins at each depth point in those profiles. So, we could forensically go through all of that.
Well, again, it depends on what level of support you're going to ask for those reflection seismic surveys, because those with a more geologic bent have expressed their issues of seeing this, seeing that, and I won't go back over my concerns with where faults are not put in, for instance. And Chris has referenced that all the interpretations on those 2D sections were as dashed lines, and then out comes in the end a solid line. This is the way it is interpretation. Again, just in terms of a comment on it, that would be my proposal to the IPRP. Is that's the comment on this onshore data. Now, whether it makes a difference depends on what you choose to pose as the consequence of those lines. And I don't know that we're there quite yet.
And that was my question to Steve earlier, was this is worth going into and really figuring out, can you rule out models? How can this really be used to exclude classes of models? Is worth diving into if it's really hazard significant, if it makes a big difference in the results. And I think the answer there was to the TI team, and it's in my experience in doing hazards, is if you have a class, you have a volume with faults in it, if you have no idea where those faults are, how deep they are, and all you know is kind of the energy budget in the system, it doesn't really make a lot of difference where those faults are in a probabilistic analysis. You have the whole range is uplifting at a given rate. You only have a certain amount of energy in the system which you can distribute on faults that are somewhere underneath there. And in that kind of world, there isn't one model that doubles the hazards compared to the other models. They're modifying the overall hazard around the margins by I don't know, 10% of the outside probably.
At the outside.
So in that kind of if we're looking at models that aren't changing the hazard very much between a single thrust fault underneath the whole thing, going to the north, going to the south, or up from the middle, which is the three models we were talking about, that the TI team is already considering, then it's not really worth figuring out whether, how good these sections are and what they do constrain, because they're not constraining hazard anyhow. So that's kind of the Did I just say geology? It doesn't matter. Where did Doug go? The transpersonal model makes a difference if you put lots of extra slip in the translational component of it. I think the north dipping thrust model, I think makes a difference if, well, only to the extent that the plant is in the hanging wall, and every earthquake gets a hanging wall factor. And so there's still things to figure out here, but I think they are on the edges of the hazard analysis. And so I'm not convinced it's worth really digging into the weeds. Sorry, Bruce. But because it's whether this is a hazard certificate or not.
Well, I think if you buy my idea that the reflection data doesn't constrain a wide range of models, maybe some other data constrains it. We need to understand what the universe of reasonable plus a margin models are, and then look at the seismic hazard all over that space. I would submit.
Well, and my editorial comment on this report was that there is a reformable cross-section, structural geology, well analysis, surface geology analysis effort in here that's expressed as the conclusion to an analysis of the seismic sections, which is really kind of tacked onto the end of. I think there's a discontinuity in that report that threw me off. I think that's kind of what my main comment on that report is that the conclusions don't follow from the geophysics; they follow from everything else you've done, which isn't really described very well.
You can move on and see.
Next topic is pass these on.
Thank you, Stu. This next presentation is going to give a very quick overview of what's in the AB 1632 report, Chapter 12. This was an additional task that was added on in the AB 1632 scope for PG&E, was to include some kind of response or addressing the concerns raised by Dr. Hamilton. And so I'll be giving the presentation. I'll be representing Bill Page and several other contributors who pulled together a review of the model, of data relevant to the model, and conclusions that could be drawn from those data. The approach that was taken in Chapter 12 was to review the proponent models of Dr. Hamilton that are presented in the available reports. It included a testimony that was given on behalf of A4NR to the CPUC. There was an AEG abstract, a copy of which Dr. Hamilton shared with PG&E. That was from a presentation given at an AEG annual meeting in 2012. And then, most salient for the SHAC, there was a presentation given in November of 2012 at the SHAC Workshop 2 down in San Luis Obispo. So the approach was to review his proponent models and to evaluate his models against available data to review their plausibility. There are two proponent models. The first proponent model is that the Diablo Cove fault is a seismic hazard of concern for the DCPP. And as a statement, I have here, do data support the interpretation that there is a Diablo Cove fault that connects laterally with the shoreline fault, at depth with other fault sources, and that should be considered as a source of surface fault rupture hazard or strong ground motions. So that, I think, is articulating kind of the proposition that's put forward with this proponent model for the Diablo Cove fault. This is a figure that's taken from Dr. Hamilton's shack presentation, in which he shows the interpretation of the Diablo Cove Fault in the onshore, extending offshore, and then connecting at least within a very short distance of the shoreline fault that's shown by that line. The second proponent model that's put forward in the various documents that Dr. Hamilton has provided or presented is that there is a San Luis Bay / IOF, or inferred offshore fault thrust, and that it is a well-defined seismic source. And so here, the question, do available data support the interpretation of a San Luis Range IOF thrust that accommodates differential uplift of the margin of the Irish Hills in the San Luis Range in the locations and at the rates that are proposed by Dr. Hamilton? So these are the proposals, these are the proponent models. The figure that we see here is from Dr. Hamilton's testimony, and it shows, I think for the Chapter 12 report, there were some colors that were added. In yellow is the surface trace of the proposed San Luis Range IOF thrust. I should clarify the surface trace to the north and to the south. In blue is the shoreline fault, and the proposal holds that the San Luis Range IOF thrust impinges at shallow depths against the shoreline fault where the two of them coincide. Okay, so moving quickly to the results. All of these, Chapter 12 goes through a review of the data, the original data as best we could track it, and goes through stepwise. So this again is an overview. So our main results in looking at the Diablo Cove Fault. The data would suggest the Diablo Cove Fault is not active. The data strongly suggest the Diablo Cove Fault is not laterally continuous. It's not continuous in map view, and there's no evidence that suggests it's continuous at depth. And as far as for how to explain the Diablo Cove Fault, it is best explained in the view of Chapter 12 is that it's a shallow Miocene to early Quaternary fault that developed in relation to the folding from the earlier fold phase of deformation that are recorded in the tertiary strata throughout the Irish Hills. The figure that's shown here is that there'll be a comparable figure shown soon, but this compiles all of the data that were collected during the investigation phase and during the excavation phase for Diablo Canyon Units 1 and 2. The Diablo Cove Fault was originally identified along the outer coast. Later, during trench excavations and then the foundation excavation exposures, there were additional faults that were mapped in this area underneath the turbine building. That part right there, and I believe some other traces there under Unit 1. And then there was some additional faulting that was noted during the mapping for the access road up to the switch yard. And so these are the elements right here. Small places beneath Unit 2, under the turbine building, and out of the coast. These are the various faults that collectively have been termed the Diablo Cove Fault by Dr. Hamilton. So the first main point, and this is a point that does not seem to be really, it's not a point at which there is disagreement. The available data, I guess I should take one step back. We have these cross sections A prime, A prime, B primed, CC primed, and DD primed. These are the approximate locations of the cross sections that are shown in the following figure. This figure was presented by Dr. Hamilton during his Workshop 2 presentation. And the observation that was made at the time of the sea cliff exposure, during the time of the trenches that were completed prior to the excavation for Unit 1, are that in locations of opportunity, the faulting was not observed to displace the marine terrace deposits or the wave-cut platform surface that overlies the deposits. So at the original headland exposure. There was an Arizona faulting that was mapped within Obispo Formation. There were overlying marine terrace deposits. There is no documented, and it was clearly stated that there was no evidence that those marine terrace deposits were offset, nor was there any indication of offset of the wave cut platform surface. And I believe it was the same for up here, where we have the various minor faults that were documented during the trench phase, and in places where there were stratigraphic relationships between those faults and the overlying marine sands, there was no observation of offset of those marine sands. Another key result is that the Diablo Cove fault is not laterally continuous. This figure is from the original excavation mapping. There was a document from PG&E 1974. Digitizing of the strike and dip data that are present in this, documenting or digitizing all of the fault data that were collected and cleaning those up. We have a cleaned up figure that's presented in Chapter 12 for review, along with the copy of that original document. And it shows that not only are there recognized strands for a north dipping Diablo Cove fault, I should point out that here north is more or less up and to our left, but there is the documented absence of faulting in between locations where faulting was observed here, and then where minor faulting was observed here, and then again here. And there are other features such as fracture zones that were logged and identified, and there were exposures in between traces and exposures behind where the absence of faulting was documented. The amount of offset that was documented is on the order of 2 to 5 feet or thereabouts. So these are within the same Miocene unit. These are offsets where there were offset equivalents that were interpreted, and they were shown to be on the order of a few feet. There was documentation from the time that showed the absence of lateral continuity, and all of this is based on direct observations onshore. Now, offshore, part of the exercise was to look at the recently acquired seafloor multibeam data. There were additional data that were collected from an innovative system called the kelp fly, where there was a multibeam unit that was mounted on a jet ski so it could go into the surf zone into very shallow areas. And so one of the additional pieces of information that we received from the 2011 to the 2012 timeframe was we have excellent, very detailed multi-beam bathymetry underneath Diablo Cove that supplements the onshore LiDAR data. This is an artificial shaded relief image of those data. Artificial sun angle is to the north. That should be optimal for highlighting any possible east-west trending lineaments. I'll advance to the next slide to show the faults that were documented onshore and observations that we interpret in the offshore. But before I do, this is about the location of the sea cliff exposure of the Diablo Cove fault. Here's the portion of the turbine building, and here's Unit 1, where the other pieces of the fault were documented previously. The trend of the faulting in the onshore, the trend of the faulting specifically where it was documented in the sea cliff and across the wave cut platform by Johns originally, showed that it had a trend that would project through the data right around in this area. Our interpretation of the data are shown here. So again, onshore in the gold lines are the locations of where faulting was documented. Chapter 12 includes a description and these annotated figures that show possible locations, possible alternative locations of where there could be an offshore geomorphic expression of this faulting as it continues offshore. Whether or not this fault would produce some seafloor lineaments or a seafloor expression is a matter of debate. In the original excavations, in the original exposures, there was no differential erosion that was noted right along that top wave cut platform surface. But nonetheless, the trend of the Diablo Cove Fault, where it was last seen before going offshore, was documented to be in about this orientation. That goes through this field, where it's possible that there are small discontinuous lineaments that could be made a case that they go through the data. They go into what we see as a very nice continuous lineament that connects a mapped fault that we informally call the Headland Fault to the north. It has continuity seen in the offshore as a very clear lineament. So from the strike of the Diablo Cove Fault, where it was last seen before going offshore, it heads into this field and then it heads into this fault. If we take an average strike of the pieces of the fault as they've been mapped here and back to here, we again come up with something that where we would infer it to intersect somewhere in here, where again we feel like there is this through-going roughly north-south headland fault, and we don't see any evidence that that is offset either. Now again, let's keep in mind that the total documented offset of this feature is on the order of 2 feet in Miocene rock. Okay, so the offshore MBS data shows a lack of continuity across Diablo Cove for any such Diablo Cove fault. Going to a little broader view, so zooming out in scale, this feature right here is the shoreline fault, or the escarpment that's associated with the shoreline fault, I should say. This is its geomorphic expression in the seafloor. Here is the turbine building, Unit 1 and Unit 2. So it's in this area where the Diablo Cove Fault is documented, or where faulting is documented to occur underneath the turbine building and underneath Unit 1. The interpretation presented in I guess the relevant documentation here to go against would be from the SHAC Workshop 2 presentation after Dr. Hamilton received the kelp fly information. But the interpretation at the time, or the proposal put forward by Dr. Hamilton, is that the Diablo Cove Fault, when it hits the shoreline, would change strike, go around the headland, and then connect with some lineaments that are shown in the offshore. Our review of the data that we have, both from the map data, the quality of the interpretation that he's put forward, and in the face of all the other alternative interpretations and alternative lineaments that are very clearly visible in the seafloor data, shows that it is not a compelling hypothesis to link the onshore discontinuous traces, much less through Diablo Cove, but connecting them to the offshore shoreline fault it's in our view quite a stretch. That's addressing the lateral continuity of the fault and whether or not there's compelling data that would suggest it connects to the shoreline fault. Another part of continuity is that there was some suggestion in documents proposed by Dr. Hamilton that this fault continues at depth, and there's some indication in the microseismicity that this fault is present down to where earthquakes or microseismicity is occurring. Our assessment of that is that the purported seismicity, as best as we can interpret from the documents given, that the earthquakes that are alluded to that are in the hanging wall of the proposed Diablo Cove Fault, it is not defensible that these earthquakes would be located on this structure as proposed by Dr. Hamilton. So what I'm showing here are the Hardebeck 2010 relocated seismicity. These were the data that were available to Dr. Hamilton at the time of his written testimony. This is the trace that he presented at the time of his written testimony, and circled in red are 3 of the small earthquakes that our read of his original testimony report are earthquakes that he attributed to possibly be occurring on the fault. I'm going to switch to another view. This now is from more recent relocated microseismicity by Dr. Hardebeck, plus an alternative interpretation of the Diablo Cove Fault that Dr. Hamilton presented at the SHAC Workshop 2. And this, again, was after additional data was introduced, the kelp fly data. These are the same earthquakes relative to the new interpretation. So we're going to go from these map views to cross-section views that are cross-sections drawn perpendicular to the shoreline fault and approximately perpendicular to the Diablo Cove fault. In red, down here, are the exact earthquakes that plot on the hanging wall side of the Diablo Cove fault when reviewed in map view. This structure here is Dr. Hamilton's proposed San Luis Range inferred offshore thrust. This is the best we can do to infer what his interpretation would be of the Diablo Cove fault at depth, where he shows it to be undocumented and consistent with the surface observation that it's approximately 45-degree north dipping fault. So clearly the earthquakes in question here that plot in the hanging wall of the fault are much more likely associated with the shoreline fault at depth and are not very compellingly correlated with the proposed Diablo Cove fault. These are from, this is the relative geometry that's shown from the 2010 Hardebeck seismicity and the original interpreted Diablo Cove fault that was presented in the written testimony. This next slide shows after additional relocation work by Dr. Hardebeck and after additional data was introduced, again, reconstructing as best we can of what the down dip geometry might be of that fault as Dr. Hamilton presented at Workshop 2. Very little change in the location at depth from the microseismicity, clearly divorced from any reasonable proposal for what the Diablo Cove fault would be at the surface. So the contention that there's evidence in the microseismicity for the Diablo Cove fault being active, we don't think that that's a defensible interpretation of the available data. The Chapter 12 report goes into some ideas of what the Diablo Cove fault is. There's an evaluation of some of the collected seismic reflection data. There are some cross-sections that are put together from the abundant strike and dips that are available from the excavation mapping and from the sea cliff exposures. And in Chapter 12, we described that we think that a fault that is laterally discontinuous, that has displacements of on the order of 2 to 5 feet, that does not show any indication of offsetting marine terrace deposits or wave-cut platform surface, is much more likely associated with the fold, the episode of fold deformation that these rocks were subjected to that started in the Miocene and has continued into the early Quaternary. And this is an episode of fold-related deformation. Fold-related deformation is commonly associated with minor faulting. So we interpret that these fit into that context very nicely. The next hypothesis, or the next proponent model that we'll investigate, is the San Luis Range, Iowa thrust. The findings that are presented in Chapter 12 was that specific model attributes are inconsistent with several data sets that are available to us for review. And again, the specific model attributes proposed by Dr. Hamilton are not supported by several data sets. So we conclude that the specific model, again, is not compelling, but general model attributes that he puts forward in the San Luis Range, Iowa thrust hypothesis we think are compelling and clearly warrant consideration in a seismic hazard assessment. There are some first-order observations that Dr. Hamilton brings that are ones that we consider to be technically defensible and ought to be explored and vetted and part of the source characterization. So again, in map view, the San Luis Range inferred offshore fault is interpreted to include the Wilmar Avenue fault. Offshore, it's interpreted to connect and start to impinge upon the shoreline fault at a location south of San Luis, San Luis Hill and Point San Luis. For the reach of the shoreline fault that includes the reach opposite Diablo, the interpretation is at very shallow depths, the San Luis Range IOF impinges on the shoreline fault. And then to the north, it's interpreted to diverge from the fault, and a structure that in the shoreline fault or the shoreline fault report was referred to as the North 40 West Fault. More recent AB 1632 reports of the Point Bouchon data call that the east branch of the Point Bouchon fault zone. This fault is interpreted by Dr. Hamilton to be the reemergence of an northeast dipping San Luis Range IOF thrust that he interprets to be at shallow depths and dipping on the order of 30-35 degrees. So in cross-section view, this cross-section blue line right here is the line of section that Dr. Hamilton has put together. This is from his written testimony. And it shows in this view a San Luis Range IOF thrust beneath the Irish Hills that is impinging on the shoreline fault at shallow depths, and the Los Osos fault being a secondary or ancillary back thrust to it. So, looking at his data closely, an important tenet of his model is that the San Luis Range and Irish Hills are a pop-up wedge between the San Luis Range thrust and the Los Osos fault. And the slip rate that's provided for the for this structure is on the order of 0.4 millimeters a year. I forget exactly what, but it would have to be. To justify it, it would have to explain the totality of the relative uplift of the Irish Hills, which is uplifting on the order of 0.2 millimeters per year, and have the footwall of the structure be either zero or subsiding. And we contend that a review of the available multi-beam data, lake quaternary geologic data from the terraces, and interpretation of different reflector packages and the seismic reflection data is that the uplift rates for the Irish Hills and the San Luis Range follow a pattern where in blue, these would be our highest uplift rates that get to uplift rates on the order of 0.2 millimeters a year. We have another belt of more intermediate uplift rates that are on the order of between maybe 0.1 and 0.18 millimeters a year. Areas of low but positive uplift rate that would be on the order of 0.5 millimeter a year, or 0.05 millimeters a year. I've got to remember my decimal points. And then we have locations where we document subsidence as recorded in the seismic reflection data and the accumulation of lake quaternary sediments. And we see these across the Hosgri Fault. We see these as we get into the offshore or the offshore extension of the onshore Santa Maria Basin, and we see these very locally in pockets such as the depression of the southern part that underlies the southern part of Morro Bay. And this pattern, even though it is shown dashed and a lot of these are queried lines, it is not compatible with there being a boundary between 0.2 millimeters a year and less than 0 millimeters a year that would coincide with the surface trace as proposed by Dr. Hamilton, which would be over here at the Wilmar Avenue, which would follow the shoreline fault, and that would follow this east branch of the Point Bouchon fault up and down. So the best available data we have about the uplift rate patterns surrounding the Irish Hills are not consistent with the proposed uplift rate pattern that Dr. Hamilton will predict. This goes into a little bit of detail. You can read about it in the report. This was also presented in the shoreline report. The location map is here, just offshore Point Bouchon. This is where the east branch of the Point Bouchon fault diverges from the other part. This is where, in Dr. Hamilton's model, one would predict the San Luis Range IOF to diverge from where it impinges on the shoreline fault. So this is where we would expect that maximum amount of relative vertical displacement to be expressed just about at the surface. Here is the geomorphic expression of the fault. Here are two profiles, A prime and B prime. B prime being located across where there is a west-facing escarpment. A prime being in an area where it's interpreted that there is a lake quaternary wave-cut platform that's inset into the overall shallow portion of the offshore shelf. So these labels show North 40 West, Now the parlance is this is our east branch of the Point Cochon Fault. In Dr. Hamilton's model, this is where the San Luis Range IOF thrust would be. We see rock exposed with no apparent vertical separation. Here along the B prime, we can see the signal that presents that very nice seaward facing escarpment that coincides with the North 40 West Fault, but overall we're not seeing a very compelling boundary, again, that would be the full amount of uplift of the hanging wall against a subsiding footwall. It's just not consistent with the best available data that we have. This is of the similar analysis at the very southern end, where the San Luis Range IOF would be impinging on the shoreline fault to the south. And I won't go into details here. Another piece of the hypothesis is that the San Luis Range IOF thrust is very well expressed in the available microseismicity data. It was put forward that this is, I don't want to use the word obvious, but is a very compelling geometry that anyone might deduce from looking at from the microseismicity data. These are different cross-sections of the microseismicity. Again, all of this is in the Chapter 12 report for you to review. These are different transects across the Irish Hills showing microseismicity, the uninterpreted and then the interpreted versions. And Dr. Hamilton notes some alignments of the microseismicity that are seen by multiple investigators. So for the shack, as far as the TI team is concerned, we see these types of alignments, we see these types of fabrics. The contention, I think, or I guess the point of disagreement is whether or not these are compelling. Are these compelling enough to require this to be some sort of unique interpretation that ought to be carried forward in a seismic hazard analysis? Our evaluation would suggest that alternative hypotheses are as viable, if not more, than very specifically what Dr. Hamilton proposed. And we'll show that, or I think additional information that we received during our workshop 3 was that independent assessments of fitting planes, trying to do a very objective approach to this type of analysis, shows that the general solution might be tenable, but the specifics of Dr. Hamilton's proposal are not. That again is laid out in Chapter 12. So one example of an alternative hypothesis, an alternative view of the microseismicity that's presented in Chapter 12 is that, well, if we look at just the spatial association of where the micro-earthquakes are compared to where there are faults that have been interpreted in the AB 1632 reports, we can show that there's a good just spatial association. Microseismicity is occurring in and around faults that are identified in the data. And Dan, you can interrupt me if I get off track. What we show here is a full box where we've extracted earthquakes and some earthquake statistics are shown. This line right here subdivides this volume into an area north of here is where the ONSIP team and the onshore seismic reflection data interpreted these intergraben sets of faults and other faults that were associated with the Los Osos. To the southwest, in between here, the only major structures that were documented are the shoreline fault zone that has a clear seismicity trend and the more east-west trending San Luis Bay thrust. And the evaluation showed that far and away the earthquakes are associated spatially with where we identify faults, both underneath the Pismo Basin and in and around the Los Osos Fault, and spatially associated with the San Luis Bay. The analysis that Dr. Hardebeck presented at our workshop 3 in March used a quantitative approach to look both at spatial patterns and to look at compatible first motions. So the energy, the origin energy that's released from these earthquakes was considered in addition to just its spatial location. And this approach is a quantitative, objective approach that has some standardized strike uncertainties, dip uncertainties. It assumes as a precondition to this approach that these small micro-earthquakes that are on the order of magnitude 1s and 2s do align to form laterally contiguous structures. And it does not in detail support the very specific San Luis Range, Iowa thrust hypotheses. Okay. Again, the general tenets of it show that southeast virgin type solutions are viable. So just as with other data that we're considering that there is some, there's definitely some basis behind the observations that those micro-earthquakes can be interpreted to show that there's a north trending structural fabric underneath the Irish Hills at seismogenic depths. Okay, the last piece of information that's presented in Chapter 12 is using the recently acquired seismic reflection data. And this is from a little piece of a 3D volume, a few arbitrary lines extracted through that volume were put together. And they were processed to try to see whether or not there are reflectors, reflector truncations, anything in the seismic data that would either support or preclude Dr. Hamilton's specific prediction of where the San Luis Range, Iowa thrust would be as it's predicted to dip north and underlie this southern portion of the Irish Hills. First is the geologic map. Next, I'll keep the same map, and this is a map showing magnetic, the total magnetic field. And one of the major points here is that there's a structure that we informally call, and for this report, the Irish Canyon Fault, that is subparallel to the San Luis Range, the San Luis Bay Fault. And this has a very clear expression in the magnetic susceptibility data. There's a big magnetic anomaly. Geologically, this is the same fault, and it forms a crustal boundary where we have Franciscan to the north and dominantly Cretaceous sandstone to the south. And so the point here is we have a structure, a targeted structure, that is clearly seen in other geophysical data. And so we predict this to have some sort of continuity with depth, saying that the signal that we're getting is this is a kilometer scale feature. San Luis Range, Iowa thrust to be. And the interpretation of the data would show that coincident with the Irish Canyon Fault at the surface, where we know there to be a fundamental crustal boundary, the interpretation was that there was a different domain of certain reflectivity characteristics that was juxtaposed against a different domain, and that domain boundary was seen, was interpreted to cut through the area where Dr. Hamilton's thrust fault was proposed to be. So that's from AA primed, and then BB prime, there was a similar interpretation of the data provided. Here are some summary slides showing the seismic reflection data that were collected and interpreted, showing inconsistencies in detail between Dr. Hamilton's proposed drawing of the San Luis Range, Iowa thrust, and then the intermediately dipping back thrust Los Osos. So showing that there's differences in the predicted dips versus what was interpreted from the available seismic reflection data. And so this again is the same AA prime. It's not a different piece of information, it's just a different demonstration of it. This is line 204 that was discussed at Jeff's talk, which suggests for a steeper back thrust Los Osos fault under this model. And again, moderately dipping back thrust, the interpretation is for a steeper fault, and then a moderately dipping San Luis Range, Iowa thrust, and that shallow depth and that gentle a dip would appear to be precluded from the interpretation of the data. Okay, so the implications for hazard in Chapter 12, the conclusions were that the Diablo Fault is not a seismic source. It's not a source of seismic hazard to the plant. The San Luis Range, Iowa thrust was not seen as a defensible model as specifically presented, and it's not suitable for use directly in seismic source characterization. Aspects of the model are quite valid, and they're captured within the San Luis Bay fault source that PG&E has had for quite some time. And that comparable geometries are, one last point with the implications for hazard is that comparable geometries that are proposed for the IOF thrust are considered within consideration for our aerial source zone in the SSC that's being developed by the shaft. Okay, so that's what I have.
I think we are running a bit behind, so I think we probably should move on with Dr. Hamilton's presentation on the same topic, and then questions for both. Does that work? Sounds
good. Can I be heard okay? Okay, members of the IPRP panel, other persons involved here. I'd like to thank you for this opportunity to be here and say a few words, and I'll try to make them as few as I can, particularly noting the time. But in any case, I guess I'm here in part because the Public Utilities Commission has asked that there be consideration of the testimony that I've given them on a couple of occasions, and a determination of whether my concerns as expressed in that testimony have actually been adequately addressed by the several programs that PG&E has underway. Those programs, in some cases, been underway since the long-term seismic program, and they include several very useful activities in terms of characterizing the tectonics of the Irish Hills and the plant site. Those include especially the installation of the local seismic network, looked over all these years by Marcia McLaren, and the data provided to the USGS for their use, including that by Dr. Gene Hardenbeck. That's been very helpful. In the current program, especially as it relates to the onshore work, I think that the onshore seismic reflection work of the several kinds that were employed by Fugro have probably yielded better data than I believe Dr. Gibson has given it credit for. I've spent actually a couple of months now living with that data, and to quote Gary Green at the previous IPRP, it's really fun having a good data set to work with. So that has been a goodly part of my activity leading up to this opportunity here. Historical note, at the time the long-term seismic program report was completed in 1988, the NRC asked 3 independent reviewers for their opinions of what was contained in that report. Those people were Dr. Robert Brown, who was the senior man on the USGS Western Regional Office at the time. It was Dr. Bert Slimmons, who is professor at UNR, and Dr. Katie Aki, who was a world-famous seismologist on the staff at Caltech. They worked independently, I believe, and they each wrote individual letters to the NRC, and those letters tended to have a common theme. They were all concerned about the seeming downgrading or near absence of consideration of compressional faulting, reverse faulting, thrust faulting, any kind of thing beyond emphasizing the, at that time, Hosgry fault. The shoreline of fault, of course, was there, but represented in the LTSP only as a line indicated as lineament. So that information that they had derived from reading the LTSP gave them all the impression that compressional faulting was basically poorly represented at best. Dr. Brown also mentioned the Honolulu Tidewater well log with evidence for thrust faulting in the form of the triple repetition of identifiable tuff layers in the Obispo Formation. So the Obispo once again came up in the, I think it was about 77-page review that Professor Yates was retained to prepare for this current report. And Yates also dwelt at some length on the implications of the apparent doubling or trebling of the stratigraphic section in the Honolulu Tidewater well, which cannot be accomplished with normal faulting. So that was a theme that has essentially lingered, and a theme that, unless it's somehow or other addressed in ways that I haven't seen, is still more or less a subject not to be discussed hardly by the team that's doing this work. So that leads me to the kind of the answer to the PUC issue is, which is are Dr. Hamilton's concerns in turn basically answered by the new research and so on embodied in this report. My answer is that my concerns now have been greatly exacerbated in two ways. First, by the, you might say, the diversion of effort to writing, what was it now? 82 pages, plus 55 figures of discounting my previous interpretations, and another 40 minutes of doing the same thing orally. So that's a lot of effort to get rid of my ideas, which makes me think that maybe they're actually important enough that effort should be made to get rid of them if you don't want to hear them. The second concern I have is that the data that have now come out and been nicely presented in the ONSIP report, especially when taken with the seismicity analyses that Dr. Hardebeck has made in the analyzing the microseismicity local to the San Luis Range and the Irish Hills, together with the obvious geomorphic expression of the hills and the geology information and other various geophysical information that is now in place, allows, I believe, a further evaluation, you might say, of what the hazard actually is. So I base this now on simply concentrating on the area of where the San Luis Range IOF would come out, which is along the southwest face of the overall Irish Hills, and the area of Diablo Canyon in particular here, with the data to be considered, including the overall determination of earthquake hypocenters represented in particular previous to the Shack 3 meeting in March by Dr. Hardebeck's having constructed 17 different transects of hypocenters across the axis of the range, running from San Luis Obispo Bay to Estero Bay up here. That then has been augmented, I think, by the material that was partly shown by Dr. Thompson as the characterization of different seismic source panels, if you will, and by the series of 3 profiles, one in Estero Bay, one just about in the area where line 141, 142 is run and where the Honolulu Tidewater well is. So we've kind of got 3D coverage in that area, and one in San Luis Obispo Bay down here. The seismic reflection data that I will use in this discussion is that of the line 112, 140, line 113, line 114, which together I think pretty well illustrate the fault conditions in Point San Luis and continuing on up the range front. Then we have the actual version of 141, 142 that was presented during the Shack 3 meeting by Dr. Unruh. And that line, unlike those that were described today and included in the ONSIP report, actually starts right at the headland at the north end of Diablo Cove and continues all the way to the Los Osos fault on the northeast side. And I found that the reprocessed version of this line seems to me to be much less indicative of likely geologic conditions than the overall line, so I have used that in my interpretation here. I would further mention that line 115 up here is the one that Dr. Nishenko spent 8 minutes at his address to the seismic safety group down in San Luis Obispo, giving preliminary proof that there was no such thing as the offshore extension of the Diablo Cove fault, not mentioning in that presentation where that line was. It is in fact quite far distant from the point where the version of the Diablo Cove fault that I believe exists joins the shoreline fault, and consequently is totally irrelevant to whether there is or isn't a Diablo Cove fault. So that's sort of the introduction to now my take on what conditions are that kind of represent maybe the closest thing to that, what was it called? Unique model that Dr. Nishenko spoke of. And I think that we're actually closer to that than we had been with all of the material that's come out during this presentation and in the reports that it's based on. So I'll now go to first the sort of the extract, if you will, of the faults that I see on the drawn as surface outcrop faults on the ONSIP map, figure 5-2, I think it is, along with the seismic lines, including the ones I refer to, which is 112, 140, 113, 114, and the west end, or the southwest end of the March version of the 141, 142. I'll start out now with my take on the interpretation of the lines at the San Luis Bay area, or San Luis Bay, Port San Luis. Now, the first of those lines, 112, 142, is shown here with my interpretation of the faults that can be discerned on that, and I don't expect you to see them, but I'm pretty sure they're there. So this is the uninterpreted data. This is my interpretation of that data, which includes a set of moderately dipping thrust faults, starting with the San Luis Bay, possibly the beginning of the Olson Trace, the San Miguelito fault here, displaced, because I think the San Miguelito fault is much older than the thrust faults that form the range front nowadays. The what I call the Point San Luis fault that is necessary in order to create the uplift of Point San Luis, which is somewhat independent from the uplift of the overall range front, and the underlying San Luis Range IOF trace or surface. I took then that interpretation, and that is this area here on the plot that Dr. Hardebeck makes for that area. And with those 17 hypocenter plots that she made, there's one basically in any area that you want to look at. On that, showing this group of events, these are she didn't specifically draw these, but these are my interpretation of the lineations of the hypocenters that one can discern in the crust and basically the spatial relation that such hypocenters projected up to the level of the seismic line show. And so it turns out that, as nearly as I can tell, there's an excellent correlation between this interpretation of a stack of reverse faults along the range front and the underlying seismicity. Moving on to line 113, next one up the coast, basically the same thing. A packet of the same reverse faults now carried along strike, visible in the line 113, and again seeming to give quite good correlation with the next set of hypocenter profiles. So these profiles, as I think perhaps Dr. Thompson pointed out, differ in detail, but they all show, to my mind, a quite consistent pattern. This, by the way, is the shoreline fault here. Then continuing on up coast, here's now line 114, just at the southeast end of Patton Hill. Again, same pattern discernible in the seismic reflection line, and same pattern really in the underlying hypocenter plot. And in all of these cases, the Los Osos fault is there only by projection from its surface trace down to using the dips that I believe are shown in the seismic reflection lines across that fault. So that gives us this lines, but they're not supported by the same kind of active seismicity that you see on the underlying thrust system. Okay. Going now to the area of Diablo Cove, which is north, of course, of the, oh, I'm sorry, this is the surface area of Point San Luis. So here again are the faults as drawn at the surface, and here is the set of profile lines. Now moving on up coast, we now come to the Diablo Cove area, where Dr. Thompson has shown all the reasons why this line of faults following, I believe, quite strongly defined lineaments in the erosion pattern of the bedrock platform seem to exist, to my eye at least. And these define essentially a crow's foot pattern of splays from a single fault line that I believe splays off of the vertical shoreline fault and comes off by necessity as a vertical fault. And then one branch, the north branch, goes into the next cove to the north, which in the past I've called the wastewater holding pond fault because that facility was formerly in that area. The central branch, which is the one that we've heard lots about, that was found in the foundation of Unit 1, and the south branch, which comes down, splays off, again divides into two branches, each of which comes ashore in a long mapped, starting with Professor Johns in 1966 and continuing on through the most recent maps that the Lettuce people have done in their work for the ISFI site and so on. And so we have now this south branch of this fault that goes into the sea cliff just at the south corner of Diablo Cove, and the next one goes into the area that was trenched up here. And so that is the fault pattern that I discern in the surface of the area of the Diablo Cove. Now, the line 141, 142 looks like hash as seen in this projection, but studying it closely, I came up with this interpretation. Once again, a pattern of a stack of thrust faults with the Los Osos fault actually imaged in it, coming from its surface trace here down to terminate on the faults that are, in my interpretation, cutting through this section and approaching the surface really, either of the shoreline fault, which is here, or along the shoreline with Diablo Canyon sitting directly above this system of faults. So having made that plot, I then independently superimposed the lines of quantitatively interpreted and defined seismic source planes that Hardebeck showed in the SHAC meeting in March of this year. So at the same scale, these two surfaces here project into the bottom part of the seismic reflection imaged panel here, and they seem to match quite well. In fact, when I showed this same drawing to Dr. Hardebeck, she said, well, she was a little doubtful about actually showing two faults. So she was kind of relieved to hear that there was some kind of independent confirmation that there were more than just two planes or one plane in this patch of hypocenter earthquakes. Okay, well, given that, we now have to reiterate the faults here in the Diablo Cove area, including the one that goes into the sea cliff at the south corner of the cove. We have the faults here, which, according to my thinking, actually constitute this series of reverse faults, including the one around Point San Luis. But we have a gap in between, 2.5 kilometers, with no seismic lines that I'm aware of, unless one counts one that I think was run up the coastline, and that wasn't mentioned today, but I believe that there was talk of that in one of the earlier SHAC meetings. In any event, there's a gap between these variously mapped and identified faults and the area in between. So now we look at that area, and we see that although there's a gap here, the range front, that continues quite along without any change at all. It has the same facet truncated fault line scarp type termination of spur ridges that come down to the shoreline in between the area where the three lines I showed, and this is the line 114, the closest going north, and the Diablo Cove faults up right here, which are going south. So no change in the range front. We look at the hypocenter profile that goes through that area. No change in that to speak of other than in detail from the hypocenter profiles either to the south or the north. So that leads to a glitch here in the system. That leads to this interpretation. So here now we have, or at least I, have filled in the gap using the arguments that I've just presented, the continuous range front, the continuity of the pattern of hypocenters, the recognized young thrust faults to the south, and the faults in the Diablo Cove area to the north, including the one that passes into the sea cliff just at its south corner. So if it turns out that somehow or other this should be the actual or the unique representation of seismic hazard in this area, what we have is probably what would by definition of NRC criteria is a capable fault that runs right up to the terrace, right at the foot of the range front and right into Diablo Cove, with one branch going through the Unit 1 turbine generator and into its reactor, whether continuously or not. There certainly are fault breaks there. And with the south end being faults that have long been accepted ever since the long-term seismic days as recognized seismic sources here, the San Luis Bay Fault and possibly the other branches, the Olson Trace running on up here. So if that's the case, well, what is the consequence of the magnitude 6.7 earthquake that's in the kind of in the licensed condition is happening here, but at great depths? Well, if it happens right along the upward trace of the IOF San Luis Range fault, now we have faulting at the surface. What does it do? Well, it might be kind of troublesome if it actually breaks in the bottom of the foundation for Unit 1, and it might be troublesome if it cut off the cooling water intake, which it passes through right here. It might be troublesome if it surface faulting or violent earthquake motion disrupted the road leading in, which pretty much follows the fault track. So I leave you with that. Thank you.
That might be a different fault than what was. Other data to say something about that in our evaluation of, I think the IPRP is going to have to say something about the chapters that bear on the San Luis Range, the Irish Hills tectonic models from the report. And I'm not sure we have, this is the first time we have seen this interpretation, so I'm not sure we will have time to say much about it.
May I add that this interpretation has come to me only as I spent those last weeks studying the onset data and matching it with the seismicity data. And also may I add that I'm telling this story at a poster session at the AGU meeting on the 15th of December over here in the Moscone Center, which I expect to be a much more thorough representation of my interpretation of things throughout the area of the range.
So it's, I'm not sure if we're going to be able to say very much about this set of interpretations in our IPRP report. But this is certainly interesting, and I think we will have to say something about the Chapter 12 conclusions. And I think there's certainly a couple of questions in there, and if I might, the questions I had for Steve were the difference between the offshore, the IOF thrust and the Southwest Virgin tectonic model. Seem to be where, just in terms of where the uplift boundaries are, and also, and maybe to a small extent, slip rate.
It's right, it's slip rate. We don't have the differential uplift rate that Dr. Hamilton proposed. Instead, we're going with the observed uplift rate in the footwall of the San Luis Bay Fault compared to the hanging wall, but it's close. And the location of the source differs. In the IOF thrust model, its strike changes to where it's basically the structure contours would be subparallel to the shoreline fault. So you have
It comes up the shoreline.
subparallel, yeah, right, perfect slip partitioning.
Okay.
Whereas in the San Luis Bay Fault, it's the orientation of the thrust ramp follows the uplift rate pattern as it's best shown in the onshore and offshore data, and its direction of motion as a reverse fault is more compatible in our mind with what's known about the orientation of sigma 1, or also D3, the maximum shortening direction.
And
So-
what that really does is it puts the slip boundary farther down,
It's a greater, right.
and
the San
then
Luis Bay-
farther out, a little bit offshore.
Yeah, so
From the plant, rather than coming right up to the.
Yep, yep. So the San Luis Bay Fault, what's in the Shack model for that Southwest Virgin model, the source to site distance is greater in our model than in the San Luis Range IOF thrust hypothesis.
You have a deeper fault than what
Yes.
Doug is proposing.
Yes.
Okay, so I think that's something that we can probably say something about. It's important to be able to distinguish what the IOF is from the Southwest Virgin model to the extent we understand that. We'll say something, but it seems like, to me at least, I don't know if anybody else wants to weigh in, they seem like they're very similar models.
Mm-hmm.
and probably almost no difference in terms of their hazard implication. Just a little bit more in depth, maybe, in the few percent range. Maybe. This is a different kettle of fish, and I'm not sure we've had the chance to think about it carefully. If there is a Diablo Cove fault that connects all the way along the shore into that would be, and as you suggest, that might be significant. I would like to see data for it rather than just the geophysical sections, which I don't entirely trust anyway. Sorry, Tim.
Let me be an equal opportunity curmudgeon, and based on the long distance and the small scale on the screen, I don't see those seismic reflections constraining this model any more than they do any other one. And I would be happy to sit down with interpreted and uninterpreted sections, but my guess is, and again, my critique is on the overall image quality of those sections, allowing a wide range of interpretations. And so I think what Chris is perhaps getting at is that there's a set of other sets of data that need to be brought into the thought process, and whether that's a SHAC process or whether that's an IPRP process, as part of our comments on this particular report that's before us. I'd let Chris and others think a little bit more about it.
I think we probably, and this is something that for the SHAC team to think about, but it seems to me that there are things like terrace mapping along parts of that trace that ought to bear on the activity of that. And there ought to be good surface geology ways of evaluating this hypothesis. And
Can I make a comment, Chris?
We'll have to talk about that more yet.
The Diablo Cove fault doesn't offset the marine terraces, and certainly the San Luis Bay fault does, but very markedly. So I would separate those as two different old faults, unreactivated.
Well, and he's connected the dots here.
Yeah.
So if this fault continues on,
exactly where you put it, I agree with Steve as well. There's some uncertainties there, but it's covered in the models. But I really don't think the Diablo Cove fault's connected to it at all. I think the evidence of that is just,
I think that's.
Might I comment that Bill is right in that the San Luis Bay fault certainly offsets the terrace, and I believe it's quite a big fault, really. I believe it's part of that system that the whole range is uplifting on, whereas the Diablo Cove fault, as we have seen it offshore, is a pretty small display of a fault that I believe to be related to the overall system that includes the San Luis Bay fault. But with its 2 or 3 feet of displacement, obviously it's not a big actor. However, the terrace that it doesn't displace is 80,000 years. And if I recall, the criterion is no multiple offsets in 500,000 years. So whether you can actually squeeze 500,000 years out of that, I don't know. But the detailed photographs of the fault show that it looks like it probably did undergo multiple movements to accumulate even that 3 or 4 feet of displacement that we see in the bedrock of the Unit 1.
I think another challenge for the IPRP is in commenting on Chapter 12 of this report. We were presented with one hypothesis, and under that hypothesis, I was persuaded by sometimes more than others, but by 4 or 5 different sets of information that were relating that hypothesis. One spoke really mostly to me, is if the Diablo Canyon fault is only so long, can it project to depth? The scaling argument seemed to be a reasonable one that would be, the hypocenter information also seemed to make sense. This is a very different hypothesis.
Yeah.
And I don't know what to say about it at this point.
And I think of the two things, I think the Diablo Cove fault, I think everyone's accepting that it has a very small displacement no displacement of the marine terraces.
Of the 80,000 year
Of that, of the
the
way that
ages
flat-
of the best, yeah, the best mapping would suggest that it's the 5E, so 125.
So we have a very slight displacement since the Miocene and none in 100,000 years, plus or minus. So it's, as we said, a minor actor in this, if it has any significance at all. The whole IOF thrust fault and the interpretations of multiple thrusts from the geophysical sections, I think is something that, yeah, I think is acknowledged is a viable tectonic model. And I think what I saw in chapter 12 was specifics of the model, such as the uplift boundary at the shoreline fault and the east branch of the Point Bouchon fault are, I think, in the way it's expressed in chapter 12, clearly wrong. And I think that's pretty good support for that. But that the absence of an uplift boundary exactly at the shoreline fault doesn't disprove the postulated thrust fault. It just says the uplift rate boundary is farther offshore, which is where it's shown. And I think that's where the conclusions of chapter 12 are. We need to consider a model like this, just not exactly this model. And I think that's the question for us in writing this up is whether we think that what's expressed here is adequately covering the IOF in particular. Because I think that is there's a viable model with a thrust fault in about that location, and that certainly that sense of slip is reasonable. And so that's acknowledged in these reports, is that's part of the potential models that have to be considered. This is Southwest Virgin model. And so that model is, to some extent, the same general tectonics as what you propose. And I think it's up to us to say what is the difference, and is it important that, you know, they've written an 80-page report saying you're wrong, and then they built a model that's in terms of hazard, that's the same as what you would do. And so I think that's, I don't have a problem with that, but I think that's if their model adequately covers what you're proposing, it doesn't matter to me what you call that model. So that's. Other comments on these? So it's going to be a challenge to write this up. So I'm going to try to get done before we both show up at AGU with our posters.
Before we adjourn, we get a sense for when we want to have our next IPRP meeting. And I think there was some mention of the first week in January.
Yeah, I think first half of January is kind of my preference. People.
The
Yeah, I think
5th is a Monday, so the 6th Tuesday. Would that work?
is
The 6th of January?
6th of January. Everybody going to get their calendars?
Tuesdays are always bad for me. Mondays,
7th?
yeah. So the second full week of January, well, you know, in more toward the 18th. I mean, Eric, maybe you could put out a suggestion that somewhere between January 1st and January 15th or 20th, we could get some indication.
What days of the week tend to work for you?
Any day but Tuesday.
Any but Tuesday.
And that first Monday is also problematic.
And since this is the, I don't know, Stu, this is the site amplification, site conditions, I think it's, the schedule I think we need to work out around is probably norms.
That's right.
So that's,
Yeah, whether it is teaching obligations this spring, but
that's it.
you can take a look at his calendar. We'll,
You can try to get a hold of it.
Can we tentatively try for Wednesday the 7th. And if that doesn't work, we'll slip
I think
to the
that-
next week. Well, let's
That's
try
11, see,
the 7th. We try for the 7th.
Seventh,
Yeah, let's target that.
Wednesday the 7th, Thursday
Okay,
the
let's
8th.
try.
Thursday the 8th.
Yeah,
Thursday the 8th.
Thursday the 8th.
and then how about the following week or the following?
yeah.
The following week is fine with me as well. Wednesday, Thursday, following that.
So let's target the 8th.
There'll be no massacre, okay?
Okay, further questions? No more new faults today?
So are we done with the date?
We have a couple of tentative dates that Eric's going to send an email around, and then Stu is going to check with the key PG&E folks that have to deal with this.
So
Yeah.
much easier to sign the date.
Well, it's, yeah, but we don't have the key people in the room right now.
I'd like to thank everyone. If you have any questions, my email is eg1@cpuc.ca.gov, and my phone 415-703-5560. You can direct any questions. Thank you again. See you all at the end.